In this video, we are going to look at the recursion theorem. Earlier, we have already looked at undecidable languages. So once again, before we look at the recursion theorem, let's sort of summarize what we have learned about different kinds of languages. So we have regular languages. We learned regular languages, right? So when we learn regular languages, we also learned a way to prove that a language is not regular. So we can use fooling sets. And we can also use pumping lemma. To prove that a language is not regular. And then we look at context-free languages. And then in order to show a language is not context-free, we also have a pumping lemma for context-free languages. And then we look at decidable languages. Okay, so then how do we show that a language is not decidable? So we can use diagonalization. So that is a direct construction of an object based on an enumeration of all Turing machines under a fixed encoding. For instance, we prove acceptance, the acceptance language by Turing machines is not decidable. And also we have reductions. Okay, so these are the things that we have talked about so far. So for regular languages, for instance, if we go back, so we know that regular languages are the languages accepted by DFA, deterministic finite automata. And we also know that in terms of acceptance, DFA is equivalent to NFA. And for context-free languages, we also have push-down automata PDA, which is non-deterministic computing device with an unbounded stack memory. And similarly, we also have deterministic PDA, but we know that they are not the acceptance power. PDA is not equivalent to DPDA. Okay, the reason for that is PDA accepts context-free languages that could have inherently ambiguity, and TPDA gets rid of, and DPDA doesn't have ambiguity. So these two models are not equivalent in terms of computing power. Of course, PDA is more powerful than deterministic PDA. And when we look at decidable languages, then we look at Turing machines. So we look at deterministic Turing machines. And we also know that deterministic Turing machine in terms of computing power is equivalent to non-deterministic Turing machine. Okay, so that's what sort of in a nutshell, that's what we have learned up to now. So today we are going to look at some techniques of showing languages are not decidable. So then the first thing we're going to look at here is the recursion theorem. Okay, so let's first look at this question. Can we devise a Turing machine that ignores its input and prints out a copy of its own description? So what that means here is that, let's say whether we can construct a Turing machine, let's call it self. So we give a name to it. So self, what it does, now remember we have this Turing machine in this model. So we have a finite control plus a unbounded tape memory, one-sided unbounded, right? So, and this is self, no matter what inputs it has, it basically just prints the description of this Turing machine on the tape. Okay, so this is the description of this Turing machine named self. Okay, so that includes, we know, the set of states, the set of tape symbols, and the transition function, the start state, accept state, reject state. So that is a description of self. So it prints itself on its tape. So then we want to know whether such Turing machines exist. And the answer is yes. Okay, so here is why we have this thing. So we can first construct a Turing machine, let's call it P, as follows. So it takes input. So P will take any input. Let's say it takes input X. Then we can look at X as an encoding of a Turing machine, right? So we fix an encoding, then any integer can be decoded into a Turing machine. So then on any input, let's say this is a binary string, right? So any binary string can be treated as an encoding of a Turing machine, and hence when you read an encoding, I can decode it and get the description of that Turing machine. So that means that this X is encoding of a Turing machine. So that means that some Turing machine M. So that means we can. So this P will take on any input X that is encoding of a Turing machine M. So that is X. So then what it does is simply print this, print the description of a Turing machine that runs M on this input. Okay, so what it really says is this: it runs. So you got this Turing machine, it runs M on the description of itself. Okay, so that means that I have a description. So this description is M on input and this. So that is a description of this machine M that runs on the encoding of itself as input. So that is a description. So I output this description on its tape. So that's what P does. All right, so once again, let's just look at P again, all right? So P on input X, okay, so if you think of, you have a decoding, so that's called DC. You can think of it DC as a decoding. So DC on X returns a Turing machine. So what P really does is it outputs a description of this Turing machine on X. Okay, so this is the decoding of X. That is a Turing machine. So that means this Turing machine, so this Turing machine M runs X. So X is just the encoding of M, right? So this Turing machine runs. So decode X, you get a Turing machine that this X is the encoding of that Turing machine. So you have a description that run this machine on this. So that's a description. So this is just the same as M on this. Okay, so that's what P does. Okay, so that's another way to look at it. All right. So then, then we can. So P takes any input X, but then of course this X could also be P itself. So we let this, and then we are going to run P on this input. Okay, and then I am going to call this self. So this is self, does this. So that means that the encryption of self, the encoding of self is just the encoding of this description of this Turing machine P on the description of P itself as input. Similarly, that this P on this encoding of P as input, it really outputs itself, really outputs this. So that's self, okay? So that means now self, this Turing machine simply outputs the description of itself on the tape. So that's what it is. So once again, maybe we pause a little and think about this. So let me start from here. So what we do here is that we look at P for any input X. We think about X as an encoding. So that means I can decode X and get a Turing machine. Then that Turing machine, I'm going to just run on this input X. So that is going to be the output of P on input X. Okay, so we can think of that. Okay, so that is what it is. But and then when we put X to be the encoding of P, because for many such well, it takes any X, then of course P itself is a Turing machine. So of course there will be an input X that is exactly the same as the encoding of P. So then P on this will just be, okay, the decoding of P. So this is P, and then you get this. So that is encoding. Okay, so that is a self, what self does. So self, it just runs P on the encoding of P itself as input. Okay. So then, so this guy is a self. So next, we're going to see the recursion theorem. Okay, so now let T be a Turing machine that computes a function T. Okay, so that means for any computable function T, there is a machine that computes it, right? So we can think of this as for any computable function T, which takes 2 arguments as input and outputs 1 argument. Okay, so that's that. So this is for any, okay, for any computable function T of x comma y, there is a Turing machine R, okay, that computes a function small r such that this small r of x is equal to T of, on the description of R itself as input, so one of the input, and then x is the same as this input x. Okay, so it's sort of like a self-reference, right? So R is what R computes, so capital R, right? So capital R computes R. And this R is equal to T of, now this T is any given. So that means for any T, there is an R that computes, so this is Turing machine R that computes a function small r of x such that it is, so r of x is equal to T of the description of R and x as input. So that is the recursion theorem. Okay, so now let's see how we prove it, how we can prove it. So the proof is not hard. So let S be the following Turing machine. So this is S, which is this on input, okay, on such input, which is the first one is encoding of a Turing machine. The second element is an input to this M. Okay, so we simply run capital T on this input, M comma X, okay, where M is this thing, is the encoding of M on input, which is encoding of M itself. So that's a small m. Okay, so let's just close this. Okay. So then, so this just what this, so this is what small m is. Then by definition of T, okay, S outputs T of small m comma x. So that's what T does, okay. So it's, once again, so S is a Turing machine that on an input, so it takes this input, which is a pair of 2 items. The first item is an encoding of a Turing machine. The second is just an input to that Turing machine. So then we run T on small m comma x. That small m is the encoding of this m on the encoding of m itself as input. So that's what it is. Okay, so that's what S does. And then it outputs T of small m comma x. So that is what S does. So now let R be the following Turing machine. Okay, so for any T, we have this Turing machine R, which on input X, okay, so this R takes input X and run S, the one we just constructed. So run this Turing machine on the input. Now this S, we already have it, so it can run on its, so we know what its description is. So we run S on the description of itself, comma X. Okay, so then which outputs T, so which outputs this thing? Okay, because now this S becomes M here. So which simply outputs this. So now we let this be R of small r of X. Okay, so it's just small r of X. So now we look at this thing, okay, which is a description of a Turing machine that runs S on input. On input. So remember this Turing machine S is on this input X. Okay, so this so which will be this M becomes S, right? So that means now it's on input encoding of S comma X. Okay, then which is just R. Okay, so this R runs S on this input. So which is R. So that means this is just a description of R. Okay, so that's what we have here. Okay, so it may take a little while to sync this into our thinking, right? Because it looks, so it may be not so intuitive, but as we said, that we are dealing with Turing machines, and from what we saw earlier, anything that talks about Turing machine, right? Because we know halting problem, acceptance problem, and halting problems, and we have seen several examples that if we just want to know whether Turing machines would have certain properties, so that is not decidable. So those are not decidable. Okay, so then Turing machine has this property. It can be self-referenced, which means that I can have a Turing machine that just prints the description of itself. Okay, and so then we have this recursion theorem. Again, the how we interpret this theorem. So the recursion theorem states that the Turing machine can obtain its own description and then goes on to compute with it. So remember, the Turing machine we have is here for any computable function T. We have a Turing machine R. So that computes, so maybe I write it, oops. So for any computable function T, which takes 2 arguments as input and output 1 string, 2 strings as input. Then we have a Turing machine R that computes a function small r such that for all x, r of x is simply equal to t, and taking the description of this Turing machine, capital R and comma x as input. So that's what it means, that a Turing machine R can obtain itself and can obtain its own description, and then goes on to compute this R, because capital R computes small r. Okay? So that's what it means. So in particular, we may use the recursion theorem when designing Turing machine M by including the phrase obtain own description, okay, encoding of M in the informal description of M. So that becomes handy. For instance, we can devise self as follows. On any input, okay, we simply obtain via the recursion theorem own description, which is this, and print it. Okay, so because this is t is any computable function, print something is a computable function. All right, now let's see how we apply the recursion theorem to prove some languages that are not decidable or that are not even enumerable. Okay, so this is a so added to the earlier page. So when we talk about, remember at the very beginning, we talk about regular languages, context-free languages, decidable languages, and now we can add it to a new thing. It's called enumerable languages. So how do we prove something that is not enumerable? We can also use recursion theorem. So that's another thing. So we can use recursion theorem. Of course, we can use a reduction. We can also use recursion theorem. If a non-enumerable language is reduced to a new language, then that new language is not enumerable. That's using reductions. Then we can also use recursion theorem to prove it. So now we finally can put things together. So we have regular languages. We have context-free languages. Then we have decidable languages, and then now we have this enumerable languages. So again, for regular languages, we have there's a fooling set and pumping lemma that we can use to prove a language that is not regular. And for context-free language, we also have a pumping lemma that we can use to prove that a language is not context-free. For decidable languages, we can use diagonalization and recursion theorem. And today, we can use diagonalization, reductions, and recursion theorem to prove that a language is not decidable. Likewise, for enumerable languages, we can also use diagonalization to prove something that's not enumerable directly. or we can use reductions as decidable languages, and we can also use recursion theorem. So for these two types of languages, the tools are the same. Okay. All right. Okay, so now let's look at the first example. So showing that A sub Tm is undecidable. So remember we prove it using the diagonalization. So now suppose we have a recursion theorem. How can we prove it's not decidable? So now suppose that by contradiction, okay, A sub Tm were decidable. Then that means that there is a Turing decider, D, such that D accepts instance M comma X, if and only if M accepts X. Okay, so that's what this decider means. Now, decider means that on this instance, on this input, D will always hold. So now we construct a Turing machine B such that on input X, it obtains via the recursion theorem own description encoding of B. So we construct something that can actually get its own description. So that's really what the recursion theorem says. So it gets its own description. So then we simply run D on B comma X. Okay, so we construct B, but since B can get its own description, so we can run D on this description and X. Okay, and accept X, okay, if and only if D rejects this B comma X, because D is a decider, so we can, it always stops. When it stops, it either accepts or rejects. If it rejects, then this, then we'll accept it. Okay, so then that means this B, so this B runs D on itself, on the description of itself and comma X as the input. And if D rejects it, then B accepts X. Otherwise, B rejects it. So that means that B accepts X if and only if D rejects it. So when D rejects it means that B rejects X. So there is a contradiction. So the contradiction points to the assumption that A sub Tm or decidable is wrong. So this is wrong. So that means that A sub Tm is not decidable. Next, we're going to look at another language. So there's a min sub Tm, which is a set of encodings of Turing machine, where, so this double bar here means the length of its description. Okay, the length of the description is the smallest among all equivalent TMs. That means that equivalent means that they all accept the same things, okay, or compute the same thing. And we're going to say that it is not Turing recognizable. In other words, it is not enumerable. You don't have a Turing machine to enumerate this, the elements in this set. Okay, how we prove it? So suppose that this min sub Tm is Turing recognizable. So that means that we have an enumerator, which is a Turing machine E, that enumerates every element in this min sub Tm. So it enumerates it. So enumerator doesn't take any input, but just keeps output strings that in this set. So now we construct a Turing machine C such that on input X, it obtains via the recursion theorem the description of itself, which is the encoding of C. Then this C simply simulates this enumerator E until a machine F, okay, appears with the size, the length of its description is greater than the length of the description of C. Okay, so this F exists because this is infinite set. Okay, so this is infinite set. So it exists. So then it simulates. So this is C. Once you get F, then once C gets F, then it simulates F on input X. So on this input X. So now we can see that C computes the same thing as F because it just simulates it. So that's equivalent to C. But then C also includes the description of F. So that means that the length of the description of a C must be greater than the length of the description of F because it includes it. So then, of course, so that is a contradiction because you cannot have this at the same time. You cannot have this and this at the same time. So why it's a contradiction? That's because you assume this is enumerable. Now, once again, so this Turing machine we constructed. So this Turing machine C we constructed, which simply so first of all, it is a Turing machine. Then there will be other Turing machine that's equivalent to C. Okay, and so then of course we can say that there will be one, okay, that is equivalent, but it has its the size of it is greater than the size of the description of C. Okay, so then C computes F. So then, of course, the F and C are equivalent. Then we cannot tell at this time which one is the smallest. Because we know that once you have two, then you know which one is smallest. But here, if you try to say this is smallest, I put it in this set, then this set, of course, exists, right? So there is a smallest one, but then this set cannot be enumerable, cannot be enumerated. Okay, if it were enumerable, then we'll have a contradiction. So basically, that's what it means. So now you see the power of the recursion theorem because we can, any machine we constructed, we can assume that we can get the description of itself, okay, via the recursion theorem. So that is how we can use the recursion theorem. So let's look at one more application. So assume that if a string isn't a proper encoding of a Turing machine, it describes a Turing machine that rejects immediately any string. Okay, so this is just the assumption because any string we can view any binary string as encoding of a Turing machine, but it may not be a legal encoding. So if it's not a legal encoding, then we would just assume that is a Turing machine rejects anything. Okay, so from here, then we can have the following result that is also called a fixed point theorem. So here let T be any computable function. Okay, so now T only takes one binary string as input. Then there is a Turing machine M for which T of is, so this is the encryption, this is the decryption of M, describes a Turing machine that's equivalent to M. Okay, so this itself is an encoding of a Turing machine that is equivalent to its input M. So that is really like a fixed point, right, for T, fixed point for T. So let's prove it. So we construct a Turing machine M such that on input X, it obtains via the recursion theorem own description, which is the decryption of M, or encoding of M. So compute, because so this Turing machine M can obtain its own description, which is encoding of M as input. So then, of course, this M can actually just compute this. So then whose output is treated, so we know it is encoding of a Turing machine G. So let's just say this is another Turing machine G. Okay, so that is what this means. And then M simply simulates G on X. So M computes G on X. Okay, so then it means that M is equivalent to G because M simulates G on X. Okay, so that means that the output of this, which is the encoding of a Turing machine, which is really just G. But that G simulates M on X, so which means that G is equivalent to M. Okay. So that is the fixed point theorem. Okay, so we have seen many proofs, but that on when we study computability. Okay, so but that is just the way it is, because that's what we try to understand computability. And then you may ask, why do we study this? Okay, so we can understand why we study regular languages, because you want to build a compiler, you want to parse tokens. Okay, so that's finite automata, or that's regular languages or regular expressions. And you want to parse grammar, so that's deterministic context-free languages, so you can parse. So I can see why they are useful. But for decidability, why it's useful. So we are going to use this to look at some applications to the information theory. So what it means by information, right? So that's something we want to know. Then in chapter 7, we're going to look at something or a resource-bounded computing. Okay, so then we know that we can tie them into algorithms. So there are problems, no matter how hard you try, it doesn't seem that we can get efficient algorithms to solve them, even though they are solvable. Even though their solution can be easily verified as solutions, but finding a solution, it's really hard. Okay, so that is why we study this. Okay, so one of the reasons, not just one, this is one of the reasons we started this. But of course, it has its own reason, that is to study computability. It doesn't matter how long it takes, it doesn't matter how much space you take. I just want to know whether some problems are computable or not. So that's in its own right of computability. But then for us, we are more interested in resource-bounded computing for computer scientists, right? So we are more interested in resource-bounded computing. So in chapter 7, we are going to see how some of these stuff will be used. Okay, so that is the end of this video.